Now, these recordings are being posted on Piazza as links. Their main source is YouTube. So I'm putting this on YouTube and then I'm providing a link to them on Piazza. I hope you guys have looked at where the um, links are located. I have posted homework 1. So let me just do this. Before square paper, sure. It is due Monday, June 1st at 11:59 p.m. Eastern Time. Some of you have already worked on it and submitted it on Gradescope, which is a very good news. Homework 2 will be assigned today, later today. It will be due next Thursday. What else? Let's see. Studio 0 happened yesterday. So it was a very interesting day in that several of you had installation issues, or were not able to get the board to work. Some were a little bit funny, some were not so funny. The issues, I mean, but we got through it. As far as I know, everyone got it to work, got the softwares installed, got the board to work, and we are in good shape to start the required Studio One onwards, which means that from Studio One onwards, there will be a grade associated with your submission, with your studio exercise. Studio Zero was the use of Studio Zero was everybody is ready with everything they need for the next week. Now, one thing that I realized yesterday was that the amount of time that we have allocated for the studio may not be enough going forward. So what I am going to do is I'm going to be posting the studios ahead of time, and if they are all software based, meaning VHDL code, the board is with you, and maybe later on in the course we will have logic works, which is also a simulation. So you can start on it at any time. Some may choose to start on it maybe 2 or 3 days in advance. Some may start it a day ahead of time, so that we are already making progress towards the studio, and we use the actual studio time to troubleshoot, get checked off, and so on, so that for students who are excited about this, who are good at this, they will be getting done with the studio pretty quickly. And if there are some troubleshooting steps we need to take, then we can take that during the studio. I think that if you start the studio from scratch at 1:30 on a Monday, and if you are not very comfortable with the interface, then it might drag along. So I'm recommending that you start reading up on Studio One once I post it, so that you have a head start. And as you are getting more and more comfortable, you can adjust that starting time based on your convenience. Questions or comments about this? Okay, so Studio 0 was yesterday, and Studio 1, which is for credit, is going to start on Monday, June 1st. As I said, I will be posting it ahead of time, perhaps even later today. I'm going to try. All right. I think this is it for the announcements. We can get started. So, yesterday we were talking about conversion among different number systems. So, we talked about the decimal number system with a base or radix of 10. We talked about the binary number system with a base or radix of 2. We talked about, right, let's see here. Then we talked about the octal number system with a base or radix of 8. Then we also talked about the hexadecimal format with a base or radix of 16. Then we also talked about how to convert between these number systems. In fact, we also went ahead and talked about a number system which has any arbitrary base. For example, base 3 or base 5 or base 11. How do you convert from base 3 to base 5? Well, you go to base 10 and then use the decimal number system as your intermediate base. So we talked about all those techniques yesterday, and we just had started talking about conversion between number systems that have a base which is of the form 2 raised to n. For example, binary or base 4 or hexadecimal or octal and so on, or base 32. So all of these bases, there is a fixed number of bits. The number of bits has to be an integer, 1 bit, 2 bit, 3 bit, 4 bit, and so on. So with 1 bit, how many possibilities can you have? So if I add this, with 1 bit, bit stands for binary digit. 1 bit, you only have 0 or 1 that are possible, which means you have 2 possibilities. That's your binary number system. Similarly, when you go to 4-bit, you have 0000 all the way to 1111 as 16 possibilities. So that's your base 16 or hexadecimal. So when we are dealing with bases that are of this 2 raised to n format, where n is the number of bits, then we can use the grouping and expanding into the respective number of bits technique to convert between those specific bases. We started talking about this yesterday, and we looked at this particular example. So we went from a hexadecimal format to an octal number system. We took that number, which is in hexadecimal format, decaf. We converted that to binary, and then we converted to octal. So when we started to convert to binary, we expanded each hex digit as a group of 4 bits. And then when we converted to octal, we started grouping bits 3 at a time, starting from the right and then moving left. So by doing that, we were able to convert into base 8. So this was another way of looking at it is when you are converting between bases of the form 2 raised to n, you can use binary as that intermediate step. Now, how about when you convert from 8a 9b to base 4? For this, all you have to do is expand each digit again into 4 bits at a time. So you've got B, which is 11 in decimal. 11 in decimal would be 1011. 9 would be 1001 in decimal binary. A is 10 in decimal, which is 1010 in binary. 8 is 1000 in binary. Notice that I am writing 4 bits for each hex digit, because hexadecimal format, each hex digit should be represented by 4 bits, because in total it has 16 possibilities. Now once I do that, then I'm going to start grouping this. Now the grouping, the number of bits I need to group is going to depend on the base of my conversion. So in this case, I need to convert to base 4. I've already converted to binary, right? Because this is right now binary. Now I need to start grouping from the right in the group of 2 bits at a time, because I'm trying to go to 4, base 4. So let's do that. I'm going to zoom in on this and I'm going to start here, 2 bits, 2 bits, 2 bits, 2 bits, and done. And then I can highlight this in another color maybe. And then simply we write their corresponding value in binary. So for this guy, it is going to be 3, 2, 1, 2, 2, 2, 0, and 2. And as you can see, the only numbers that are possible here are 0, 1, 2, 3. 4 symbols, hence base 4. So let's write the answer here just for the sake of completeness. I'm going to erase this guy and say the answer is 20222 in the form base 4. Okay. So that's another example and a quick recap of what we did yesterday. Now let's start talking about some things that will lead us to arithmetic. So our goal today, main goal today, will be to talk about binary arithmetic. How can I add numbers? How can I subtract numbers? So to help with that discussion, I want to go through this exercise where we fill up this table. In the column on the left, I have decimal numbers, and my goal is to write their corresponding binary equivalent in the column of the right. So for 1, what would be the binary equivalent? It would simply be 1. For decimal 3, it will be 1, 1. For 7, it will be 1, 1, 1. 15, 1, 1, 1, 1. 31, 1. And I think you understand the pattern over here. The numbers in this particular column, the decimal column, are going 1, 3, 7, 15, and so on. And in general, they can be represented as 2 raised to n minus 1, where n is going from 0 and above. So n is an integer greater than 0, greater than or equal to 0. So when it is 0, you get a 1. When you get when it is a 1, you get 3, and so on. So in general, if you have the decimal number 2 raised to n minus 1, how many, what are you going to have in this particular column? Well, if you see this pattern, you are going to have a string of ones. How many ones are going to be there? I can say n minus 1 ones are going to be there, right? So quickly we can check. If I put in n as 2, what do I have? N as 2 means 2 raised to 2 minus 1, which is going to be 3. I got 1 1. Oh, actually just n then. Those are just going to be simply n ones. So for decimal number 2 raised to n minus 1, we have got a string of ones, n ones. So we are going to use this particular identity later on. The fact that 2 raised to n minus 1 is a string of ones. All right, let's move on. So let's start talking about binary arithmetic. Why do we need to do this? Well, because we need the computers to add numbers for us. We need them to multiply numbers for us. We want them to be able to do any sort of arithmetic operation for us. And at the lowest level, we are going to be dealing with bits, zeros and ones. Hence, we need to worry about binary arithmetic. Now, the first operation that we will focus on is binary addition. We already know the rules of decimal addition, subtraction, and so on because we have been doing this since elementary school. Even though that is very, very easy for us, we are going to revisit it very quickly just so that we can borrow some concepts of decimal addition and subtraction and apply those concepts to binary addition and subtraction because the rules for binary addition are similar. Now, if you have a very, very long binary string of zeros and ones, you can use hex notation to write it in a shorthand form because you will essentially be grouping the bits into groups of 4. So it's very convenient to do the binary arithmetic as well and to be able to represent answers that tend to be really long. For now, we will stick with binary. We already know how to do the conversion if necessary. So a quick refresher here. Let's say you want to add 87 and 56. These are all decimal, so we know this very well. The expected answer is 143. And essentially, if you expand on this a little bit, if you represent 87 and 56 in the positional notation format, which means that you are taking each digit and multiplying it with its corresponding weight, its decimal number system. So you are doing 10 raised to 0 and so on. For 8, the weight is going to be 10 raised to 1, represented is position notation, and then add them up. So when you add them up, you are getting 7, 6, 13, 8, 5, 13. But how are you representing 13? Because it's multiplied by 10 raised to 0. The thing that I'm trying to point out over here is when you add these two numbers, 7 and 6, oh, so notice this. When you added these two numbers 7 and 6, you got the answer 13. But you didn't write 13 in your sum directly. What you did was you wrote 3 in the least significant position of the answer. So the least significant answer of the sum went as the least significant answer of the answer, but you also had a carry that you included with the next position, which was over here, right? So the concept of carry. What I'm really trying to focus on is this. Say you have 2758. You start with all the way to the right, and when you add 7 and 8, you get 15. When you have 15, you write the least significant over here, and you write the most significant value of the result as the carry, right? Least significant of the answer goes to the sum. So this is the sum, and those are your carries. So this is the MSB or MSD, most significant digit of the addition of 7 and 8. This is the least significant digit of the addition of 7 and 8. So that's going to be your process. So when we do the addition in binary, we will also do the same thing. When you add numbers, the least significant bit will be the sum, and the most significant bit of the result will become the carry for the next position. All right, so I think that was I hope that was helpful. There's a question posted in the chat box. Let me read that. When converting from base 10 to base 2 in an example, when we multiply the fraction component by 2 a bunch of times, let's see, component, why do we write the answer from top to bottom when we... Okay, so the question is, why do I do it? So when I have, say, a number in binary, decimal, say 57.25. So over here, bits are increasing, right? So 5 is the most significant, 7 is the next least significant. So when I started dividing this, I write, 28 and 1 and so on. But the answer comes out like that in the reverse order. And the reason why it comes out in the reverse order is because the 7 and then the 5, those are corresponding to the least significant positions. So these should be corresponding to the least significant positions for the answer. But as you are going towards the fractional part, this is positions, say if you have this as position 0, this is position -1, this is position -2, and so on. So the way you can get this particular bit 2 is only by multiplying by 2 and then 4 and then 8 and so on. So the answer to your question is simply, the weight of that place in decimal. That's the reason why we use that particular order of multiplying and dividing. All right, let's move on and talk about, did we talk about this? Yes, we did. Okay, so let's talk about binary addition, and we are right now focusing on 2 bits at a time. So we are only adding 2 bits right now. So what could those 2 bits be? Well, they could be 0 and 0, 0 and 1, 1 or 0, and 1 or 1. So you could have these 4 possibilities of addition between 2 bits. So when you add nothing to nothing, you get nothing. That's straightforward. 0 to 1 is 1. 1 to 0 is also 1. And for the first 3 situations, there is no carry whatsoever. So let me actually call these sum and carry. I'm making 2 columns here. One is sum and one is carry. So the sum is actually that, but the carry is going to be what? When you add 0 to 0, there's no carry. 0 to 1, the sum you got as 1, but there was no carry. 1 plus 0, sum was 1, no carry again. 1 plus 1, oh my gosh, should be 2, right? I think there is a typo. Is there? So 1 plus 1, 2 in decimal. But 2 in decimal equals 1, 0 in binary. And in our discussion just now we said when you add things, you will, and if you get two bits as your answer or two digits as your answer, the least significant, in this case bit, will become the sum or part of the sum, and then the most significant will become part of the carry, which is why you see that for that particular case we have 1 becoming part of the carry and 0 becoming part of the sum. So I hope you guys are comfortable with adding 2 bits at a time. There are only 4 possibilities. You get the sum, you get the carry. This is called the famous half adder table. The component that we just looked at, or the fundamentals of that component, was the half adder, or simply HA, half adder, also called as a modulo 2 addition. Questions about this table? We'll talk more about the half adder in just a bit. All right, looks like you guys don't have any questions. Let's move on. Now, do we just need 2 bits at a time? We probably need a little bit more, right? So for example, if you had 52 and 37, well, 38, when you start adding, this is in decimal, you add 2 and 8, you start with the least significant positions, you add them, then the answer you get is 0 here, 1 there. So that was good, right? That you were able to do 2 digits at a time. That was okay. But right now, for doing the next position, you need something that can do 3 digits at a time as well. Or in our case, for binary addition, 3 bits at a time. So because we are going to have to add multiple bits at a time, like 4-bit number to another 4-bit number. So we need something that can do 3-bit addition, 3 digits or 3 bits at a time, so that you can do the sum, and then of course the carry out of that is 0. Hence, we look at the full adder. Before we do that, we will do a little bit of a deeper depth into the half adder. Over here, I am showing you the block diagram of the half adder. HA stands for half adder. As we can see, this is used for adding 2 bits at a time, and those 2 bits, I am referring to those 2 bits as A and B. The outputs are 2 of them. The one is sum, S, and carry out, C out, or carry. So a half adder is a block that allows us to add 2 bits at a time, and it gives us 2 outputs. One is the sum, one is the carry. So that's the block diagram. How about the truth table? So truth table is essentially a table of all possibilities or all possible combinations of the inputs and their corresponding outputs. So how many inputs do I have in this case? Well, I have A and B. How many outputs do I have in this case? S and C out. I'm going to separate them with a straight line, like that and like that. So my inputs are on the left, my outputs are on the right. Then I'm going to focus on writing all possibilities of A and B. We already know that 0, 0, 0, 1, 1, 0, 1, 1. So let's write those four possibilities here. The least significant goes 0, 1, 0, 1. Alternates, the most significant does it at half the speed, 0, 0, 1, 1. And if you follow this, you will cover all the possibilities between those two bits. So 2 bits, 4 possibilities. N bits, you have 2 raised to n possibilities. So for sum, what do we have? Let's write the outputs now. Sum is 0, carry is 0. Sum is 1, carry is 0. Sum is 1, carry is 0. Sum is 2, no, sorry. Sum is 0, carry out is 1. So that's your truth table of the half adder. Now let's write some logic expressions, which is the next. So let me do this check. This was check, this was check. Next is logic expression for the half adder outputs. So what I'll do is I will add another page here, and I'm going to borrow my truth table from here and start working on the logic expression. Actually, they are going to be logic expressions because I have two of them, sum and carry out. So let's work on logic expression for sum first. We are representing sum as a binary variable s. You guys have heard a variable or a constant before. This is a binary variable. That means it could have only two values, 0 or 1. So sum is a binary variable. Cout, which is the other output, is also a binary variable. Let us work on the logic expression, which is sort of an equation in a mathematical term. It's an equation that relates. Let me write that down. Logic expression is a logic expression is a relationship between input and output variables, binary variables. In other words, we are going to try to express the output variable s in terms of a and b. And then we will also try to express carry out in terms of a and b. So let's do that for s. Let's see, let's start with s. So to do that for s, I will ask you, when is s 1? When is it 1? Well, you will say s is 1 when that happens and that happens. Two places. A should be 0, B should be 1, or A should be 1 and B should be 0. So the two possibilities are A is 0, B is 1, and the other possibility is A is 1, B is 0. Now I'm going to introduce the concept of NOT gate, which is also called as an inverter, which is essentially a complement operation. What does that mean? That means that if you complement a 0 bit, it becomes a 1. If you complement a 1 bit, it becomes a 0. It's essentially a flipping operation. Flip the bit from 0 to 1, 1 to 0. And the NOT gate, which has a symbol like this, we'll talk more about the NOT gate later on, but it's a triangle with a bubble in front. X is some binary variable that goes in. X complement, bar over it signifies inversion, comes out. Let me push this also to the next page, but I just wanted to have a very quick discussion on NOT. We are going to be spending more time on this. So we now know that you can flip that bit using that simple NOT function. This is a logic function. So I'm going to cut it from here and I'm going to paste it here so that I have it for later. Let's come back here. There's a question. Should we use set notation for logic? We are going to talk about notation in just a little bit. So, all right. So when is S1? We answered that question. This, I should probably do this. Or this, right? So two possibilities. A should be 0, B should be 1. Actually, let me put it here, right? A equals 0. What does that mean for A complement? This implies that A complement is 1. I flipped both sides. I'm going to leave B as 1 as is. I'm also going to leave A equals to 1 as is. And I'm going to change B here. This also implies that B complement is 1. So I'm going to use, for the highlighted in pink, I'm going to use that, and for the ones highlighted in blue, I'm going to use this and this. Now, A complement is 1. At the same time, B is 1. So it should be AND over here, AND over there. So the two conditions where when S is 1 are, oh, sorry, that or that. Now let's write the expression. The expression for S is going to be this. S equals A complement and B or A and B complement. You see, I'm trying to make everything 1 here. But that's the expression for S. I'm using the bar over A to signify NOT or inversion or complement. I'm using a dot sign to represent AND operation, very similar to what you guys played with in the studio yesterday. And I'm using the plus sign to denote the OR operation. We will be spending a lot of time about this later on, but that is the essentially how you can take a first step into being able to write logic expression. That. Now, just so that we have this ability, let's try to see if we can, jump a bit and write, or at least attempt to write, the expression for carry out. I want you guys to think about, so with all this discussion, think about what the expression is going to be for carry out. Again, you're trying to ask the question, when is carry out a 1? And then you're starting to answer the question by looking at the corresponding inputs at that time. You guys can give me the feedback on the chat box. Very nice. So carry out is going to be A and B. The reason? Carry out is 1 only when A is 1 and B is 1. So A is 1 and B is 1, carry out is 1. Yesterday, only when you flipped both the switches on, the light came on. That was an AND gate. That's exactly what is happening to the carry out of a half adder over here. Okay, so we talked about logic expression, we talked about the truth table, and some initial discussion about how to reach at least, this is called a sum of product expression. More about this later. All right, let's come back here and then check this off. Let's do the logic diagram now. A logic diagram is essentially a schematic, like a circuit diagram, right? For circuits, you guys, we all draw up a schematic, a circuit diagram to represent all the connections. Similarly, for logic functions, we can sketch logic diagrams. So we are going to be needing some symbols. The symbols that we are going to use are, for NOT gate, you already saw this right here. There is a triangle and there is a bubble. The bubble is actually what signifies inversion. That's the NOT gate. We also need AND and OR. So for AND gate that you guys played with in the studio, in this case we only have a 2-input AND gate. It's a big D. Input, output. Let me call this, well, let me not call this A and B. It could lead to some confusion. Let me call this X, Y, and Z. So Z is X and Y. That's the symbol AND. Then the next symbol is for OR. These three combined are the set of basic gates. For OR, you have, I'm only drawing 2-input OR. You could have more than 2 inputs, an arc, and then a triangle. So that's your arc, and then that's the triangle. Again, I can use x1, y1, and z1. And in this case, the expression will be z1 equals x1, or also denoted by plus sign y1. So here, we can do this. X and y, x1 or y1. So those three combined are basic gates. So using these three and the expressions that we got for sum and carry out, we can essentially attempt to draw the logic diagram for the half adder. Let's see. Do I have that? Yes. I have already done that over here. What I will do is I will walk you through it. So how many inputs do I have? I only have two inputs, A and B. I have that expression for sum and carry out that we derived earlier. I have just copied them over here. Then you can see that I need A. I also need A complement. I need B. I also need B complement. So I have multiple lines. For A, I have one wire going down like this. For B, I have one wire going down like this. I also make two copies for there's a connection there, there's a connection there. I also make two more copies, A complement going down there, B complement going down there. So essentially, I have made two parallel wires and I have also split them into their respective complemented wires. A complement, B, and B complement. And then perpendicular to that, I have arranged three AND gates. And I have used three AND gates because I have 1, 2, and 3 AND gates in my expressions. Those three AND gates. The inputs to the first AND gate was A complement and B. So A complement came in from here, B came in from here, and you got A complement and B as the output. Then for the next AND gate, you have A and B complement. So A came in from this place, B complement came from this wire, and you got A and B complement there. Similarly, for the carry out, you have A and B. So A came in, B came in from those two respective wires. Now, once I have A and B, I am done with carry out at least. C or C out, that's done for me. And then for sum, I still need the plus, the OR operation. So for that, I have the OR gate that is implemented. So I literally take the outputs of the two AND gates and I feed them into the input of the OR gate to get my sum. That completes the logic diagram for the half adder. Now, where is all of this going? Well, essentially, I would like you guys to picture this. All of this is going inside of this guy in the block diagram. So to keep things simple, because we know the properties of the half adder, we just worry about the truth table. However, now we also know what goes inside the block diagram in terms of logic gates. Inputs are A and B, outputs are sum and carry out. All right, so that finishes our discussion on logic diagram. Questions about the half adder. So we have gone through a few things. We in fact have jumped ahead on some of these topics, which we will revisit later on. But if there are any questions right now, I can take them. Yes. So the question on chat box is the plus an R? Yes. The plus symbol, even though we are so used to using the plus symbol for arithmetic addition, in logical functions, plus denotes OR operation. And dot denotes AND operation. Dot we use for in arithmetic algebra, we use dot for multiplication. In Boolean algebra or logic functions, we are going to use dot, the product sign, as the AND operation. The next question is, in half adder, can I assume any letter without a bar over it represents 1 and any letter without a bar above it represents a 0? So you're trying to manipulate it, right? So you're trying to write. So when we do this, when we did this particular exercise, we asked the question, when is S1? So for individual terms that we had, one term we had was this, one term we had was this, we were trying to make them all once, this or this or this or this, which one is true. So I couldn't write A here because A is 0 for that. So I make it into 1. So for this, it really depends on how you are putting that logic expression together. Are you putting it together as a sum of product, which is this, right? It's a sum of products or products of sum. So we'll go into a little bit more detail when we talk more about logic expressions. But these are all variables. They don't represent a one, so they are not ones or zeros. They are variables that can go one or the other. But if A is a 0, then A complement will be 1, and at the same time, if B is 1, then sum will be 1. So logic expressions are essentially an input-output relationship. Let's see. There's another question here. We wrote z equals x plus y for an OR gate. In the textbook, it shows the inputs of 1, 1 result in 1. Inputs of 1, 1 results in 1. I am... So for the OR gate, the plus sign, that's exactly how it is represented. So that is accurate. The plus symbol is being used to represent logical OR operation. But the question is, in the textbook, OR shows that inputs of 1, 1. Yes. So the truth table of OR itself, let me write it over here. So we have not talked about the truth table for OR just yet. So for OR, the symbol is this, right? We talked about that arc and then a triangle. Let's say this is x1, x2, and y. And y equals x1 or x2. The truth table of a OR gate would be this: inputs, output, 4 possibilities because there are 2 variables, 0 or 0, false or false is false, false or true is true, true or false is true, true or true is also true. So I guess you're talking about this particular condition over here. So there are individual gates, and there is also the half adder, which is a combination of the gates. I hope that clears up your question. All right, let's move ahead here. Let's see. Now let's talk about full adder. If there is a half adder, there should be some full adder, right? Otherwise, we would just call it an adder. So for full adder, like I said earlier, we need the ability to be able to add 3 bits at a time. And the reason we would need that is because there will never be a situation where we will just have to add 1 bit number to another 1 bit number. You will most likely have to add more than 1 bit. For example, when you're adding 4-bit number to a 4-bit number, say for example, let me just set up the motivation here. Say you wanted to add 8 and 4 in decimal, and you were trying to represent this in binary. What would that entail? It would entail converting these things into binary format. So 8 is 1000 and 4 is 0100, and then you'd start adding them up. And when you start adding them up, you would go this, this, and this. You would go one at a time, left to right. And in any case, if you have a carry, then you will need the ability to be able to add 3 bits at a time. So if you have a carry here, if you have a carry here, if you have a carry here, when you're doing that particular addition, you need 3 bits at a time. Hence, we need the full adder. So for full adder, we are going to have 3 inputs. In this case, we are calling them carry, addend, and an augend. So 3 inputs. You can call them A, B, C. This carry is actually the carry out of the previous addition, the step that happened just earlier. So there are 3 possibilities, right? So if there are 3 possibilities of the 2 bits, 3 possibilities for A, B, and C, carry, addend, and augend, then there will be 8 combinations in total, because 2 raised to 3 is 8. 0, 0, 0 all the way to 1, 1, 1. And when you add these 3, what is the least sum and the highest sum? So the least sum will be 0 plus 0 plus 0. And the highest sum will be when you do 1 plus 1 plus 1. 0 plus 0 plus 0 should be 0. The sum is 0, carry is 0. But when you add 1 plus 1 plus 1, in decimal you get 3, which when you convert to binary will be 1, 1. Again, the least significant will be the sum, the most significant will be the carry. So even for the full adder, you will only need 2 outputs. Even though there are 3 inputs, you will just need 2 outputs, sum and carry out. So sum is already over here in this particular column. We will just add another column here for carry out or C out, which is blank means it is 0 and everything else is a 1. So let's look at some combination here. Let us focus on this guy. 0 plus 1 plus 1. In decimal it is 2. In binary it is 1, 0. 1 becomes the carry, 0 becomes the sum. Similarly, let's do another one here. Let's do this one. 1 plus 1 plus 1 is 3 in decimal, right? 3 in decimal is 1, 1 in binary. 1, 1 in binary means the carry and sum both are 1. So I hope you guys can, fill in all the details, but that's exactly what it is. Now I want to put all of this together with a diagram that I'm showing here. First, I would like to go through this particular case. I'm taking 4-bit numbers. The first 4-bit binary number is A. and I'm representing A as a sequence of 4 bits, A0, A1, A2, A3. These are all binary variables. So this could be 0 or 1, this could be 0 or 1, this could be 0 or 1, this could be 0 or 1. So all 16 possibilities could happen for A. Similarly, you have another number B, which is represented as a sequence of 4 bits, B0, B1, B2, B3. I hope you see that the subscript is being used to denote the position of the bit. So 0 for least significant and then 3 for the most significant, because it's just a 4-bit number. So when you are asked to add these two things, A and B, you will start off with this location. And if you are doing some, only the addition and you're not worrying about subtraction and so on, you will most likely put the carry to 0, initial carry to 0. And then you will add these 3 using a full adder, 3 bits at a time. You will get sum and carry. So I hope you see this, that this is one part of one full adder, or one position full adder. Your inputs are 3 of them and your outputs are 2. So if I zoom out here, that's exactly what is represented in this case. Carry in, I'm assuming 0. This is my full adder, the ability to add 3 bits at a time. The 3 bits are C0, the carry from the previous position, A0, B0, the new bits. Those 3 get added up to give you sum, S0, and C1. So that's happening at the least significant position, the rightmost addition. Then, as you can see, the carry out of the previous full adder actually becomes the input to the next full adder, and so on. So it's called a ripple adder because the carry is rippling through this circuit. How can we relate that to an addition process that we are familiar with? From the first addition, the one that is highlighted in blue, you got S0 and C1. Then we added the next things that we add are going to be these 3 to get that and that, S1 and C2. The next thing that we'll do is add these 3 to get S2 and C3. The next thing that we'll do is add these 3 to get S3 and C4. And that would finish our addition of the 4-bit numbers. So the result, if there was no limitation on the number of bits, the result would be C4, S3, S2, S1, S0. All of that in binary. That would be the result. So we started out with 2 4-bit numbers and we ended up with a 5-bit answer that is possible. There's no 6-bit possible here. The maximum that you would need is 5 bits for the answer. Now this will work for unsigned numbers and where there is no limitation on the number of bits, but it doesn't work for signed numbers. Let's take a look at some quick example of this so that you have a better understanding here. So I will add 2 numbers, 1101 to 1110. I'm taking 2 4-bit numbers to add them up. How would it go? You would start with the least rightmost position. You would add 1 and 0. You would get 1 and carry would be 1 and carry would be 0. 0 plus 1, 0 plus 0 plus 1 would be 1, carry of 0. 0, 1, 1 is 2, So that means the sum is 0, carry is 1. 1, 1, 1 is 1 with a carry of 1. And then this will be your fifth bit. That will be the answer. And you can check it. You can convert these guys to decimal equivalents and check the answer, whether the unsigned addition works or not. But that's exactly what we are talking about here. 4-bit full adder. That's what it relates to. Okay, so let's move on. Let's take a look at some binary addition and some potential problems that could happen because of addition or subtraction based on the representation we choose. We already did this binary addition. What do? We represent each of our numbers, like for example 5 and 3. These are decimal numbers here. We have represented 5 as 101 in binary. We have represented 3 as 11 in binary. For the sake of completeness, you can also add a 0 over here. Doesn't really matter. And then 5, 3, you would expect the answer of 8. Let us see if it works in the case of binary addition. You add 1 and 1, you get a 0, carry a 1, 0, carry a 1, 1, 1, 0, carry a 1, and then 1 comes down. And then 1, 0, 0, 0, that is your total sum of 4 bits, which corresponds to 8, and it checks out. The one thing that I want you to note over here, which is critical, is this. When you added a 3-bit number to a 3-bit number, you got a 4-bit number. Right? So that's one thing that I want you to kind of retain from this conversation, because soon you will see that things can go wrong because of how we limit the number of bits. So for example, if you said, I only have 3 bits, right? If you did that, then what would happen? Well, you would be essentially be ignoring that number. If you ignore that number, your answer is 0, which is absolutely the wrong answer. So what I'm trying to say is that the number of bits that you consider will be critical to the correctness of your addition or subtraction. Next, how about decimal subtraction? Well, we all know how to do decimal subtraction. We have dealt with what? Instead of sums and carries, we deal with differences and borrows. Right. So again, we are using the same sort of positional significance notation here to represent each digit. This is a decimal subtraction example. Now, one thing to note is when we borrow, we usually don't write that as an explicit subtraction. But in the case of our binary subtraction, it will help us to represent borrows as an explicit subtraction of a 1 for the left index, so the left position. So for example, if you're subtracting 5 and 6, you need to borrow. Well, borrow can be represented as a subtraction of -1 for the next position. That will really help us do the binary subtraction by expressing borrows as explicit subtractions of 1 for the previous, for the next position. Or if there is no borrow, you are essentially saying -0. So if there is a addition, there is a half adder, there is a full adder. If there is a subtraction, there should be a half subtractor and a full subtractor. So when you're doing a half subtractor, you are dealing with 2 bits at a time and you're subtracting them. In this case, you can have A and B as the numbers that are being subtracted. You can have D to represent the difference, and you can have B to represent the output of borrow. 0 minus 0 is the difference is 0, borrow is 0. 0 minus 1. So this is the unusual one over here, right? So 0 minus 1 is what? So let's see, 0, 1, right? So if you have to do 0 minus 1, what do? You have to borrow. Where do you borrow from? You borrow from whatever is over here, right? The previous one. When you borrow, what happens? This guy becomes a 1, 0, right? You are borrowing, which means that there is a borrow of 1. But this new number became 1, 0. What is 1, 0? 1, 0 is 2 in decimal. 2 minus 1 is 1. So the difference is 1. The borrow is also 1. Next, 1 minus 0. The difference is 1. The borrow is 0. Straightforward. 1 minus 1. Difference is 0. Borrow is 0. Now, I hope that refresher of decimal subtraction and how it relates to binary subtraction for at least 2 bits at a time was helpful and clear. Let us move on. That's the half subtractor. Let's go to the full subtractor table. In this case, we will be doing 3 bits at a time. And the reason why we will be doing 3 bits at a time is because what if we have a 4-bit number subtracted by another 4-bit number? We will need the full subtractor exactly for the same reasons as we needed a full adder. So in this case, we have 3 inputs, the minuend, subtrahend, and the borrow. That borrow is the explicit -1 that we need to represent the borrow as. And then finally, the result or the difference, right? So the inputs are 3 and the outputs are 2. One is the difference and the other is the borrow. Let's take a look at some columns here because it's kind of pointless to do everything. Let's just do this one and we can focus on maybe this one. And we can also do one more if necessary. Let's take a look. So here, what do we have? 0 minus 1. So the moment you go 0 minus 1, what do you have? The difference is 1. The borrow is also 1 for 0 minus 1. Now, you're done with this. Then you have another -1. So when you have another -1, you are essentially getting rid of this guy and becoming a 0 in the difference. So the difference will be 0 and the borrow will be 1. Next, let's do the next one, which is 1 minus 1 minus 0. Well, this is kind of straightforward, right? Because 1 minus 1, the difference will be 0. The borrow is also 0. And then when you do a -0, nothing changes. So you have difference of 0 and also the borrow is 0. Let's do the last one. 1 minus 1 minus 1. When you do 1 minus 1, what do you have? Difference is 0. Borrow is 0. Next, you're done with this. You also have a -1. When you do a -1, now you are doing a 1 for the difference because you borrowed, it became 1, 0, then you subtracted a 1, so you got a 1 there. And you also had to borrow because you were doing 0 minus 1. So the difference is 1, borrow is 1. All right, so I hope that was helpful and a quick review of subtraction, borrow, difference, sum, and carries. Let us move on to a binary subtraction. So when you have binary subtraction, say this is a good example, 5 minus 3. You have 5 represented as 1, 0, 1. 3 represented as 1 1. Or as I said earlier, you can also do 1 0 1 1. That's fine. When you start subtracting 1 minus 1 based on the half subtractor table, 1 minus 1, difference was 0, borrow was 0. The borrows are shown in green. Then you go to the next position, 0, 1, 0 minus 1 minus 0. For that, the difference is 1, the borrow is also 1. Borrow is being represented as an explicit subtraction of 1 for the next left position. The difference is 1, by the way, for this guy. Then you have 1 minus 0 minus 1. For that, there will be, the difference is 0, the borrow is 0. So that's going to be that's the last step. Then when you convert this to decimal, 0 1 0, you get a 2, which is exactly what you expected, 5 minus 3. So this checks out. This is working fine. Let us switch those numbers. 3 minus 5. Well, when you do 3 minus 5, what is going to happen? You have 3 at the top, 5 at the bottom. You start with your subtraction, rightmost place. 1 minus 1, you got a 0, a borrow of 0. 1 minus 0, difference is a 0, no borrow. And then when you do this position, 0, 1, when you do a 0 minus 1, your difference will be a 1 and your borrow is also a 1. Well, we are not going to be able to complete this because we are left with a hanging borrow over here. So that's when we actually get into trouble with this sort of representation. And to make things worse, look at the answer. 1 1 0. That is 6 in decimal. But our expectation was negative 2. That was what we expected. Now, if you notice very keenly over here, if I treated this 1 as actually a signed bit, this would be negative 2. That would be okay. So it looks like we need to answer a few questions. One is, when my answer is negative, how do I represent it? Do I need a different representation for negative numbers and positive numbers? How do I know whether my answer is correct or not? In this case, I've got 1 1 0. Is it correct? Is it wrong? Am I doing the subtraction correct or wrong? I need to be able to answer that. Bottom line is, we need a representation for signed numbers so that we can represent positive numbers, we can represent negative numbers, and also represent 0. So we are going to look at two forms of representation. One is signed magnitude, and the other, more useful representation, is 2's complement representation of signed numbers. We get lucky with the positive numbers. For positive numbers, the representation is the same in almost all the representation forms. Actually, we can also add 1's complement to this list. Which is another stepping stone to 2's complement. So actually, to go to 2's complement, we anyway need to find out 1's complement. And the difference between these two methods is how the negative numbers are represented. Let's see. If you think about a 4-bit sequence, 1 1 1 1, 0 0 0 0, 0 1 0 1, any 4-bit sequence, in total there will be 16 values. You would ideally want half of them to be representing positive numbers and half of them to be representing negative. Now I am saying half, roughly half, just because in some cases 0 will have two forms, a plus 0 and a minus 0. Even though they are redundant, we will still have it, especially in the sign magnitude representation. That is a problem. So it's, but we would essentially want roughly half of them to be positive and half of them to be negative with the 4-bit or any number of bits. So let's take a look at how we represent numbers in sign magnitude form and then 2's complement form. Sign magnitude tends to be easier, so let's start there. The most significant position we are going to reserve for the sign of the number. 0 indicates positive, 1 indicates negative. So think about the sign and then think about the magnitude. Hence the term, hence the name sign magnitude. You are keeping them separate. You are keeping them as two separate entities. What is the sign? What is the value? Plus 4 minus 4. Very simple. Other problems, we'll take a look at that later. One quick note over here: 0 0 0 0 1 0 0 0. Both of them are pointing to 0. So actually we are wasting one of the 16 possibilities. We are wasting that for the same number 0 in this case. So that's kind of a problem here. 0 has two representations. The magnitude of the number, in this case example 4, is the 3 lower order bits, because we have started out with a 4-bit example. The magnitude can be 0 0 0 all the way to 1 1 1, so 0 through 7. The sign can be either positive or negative. So if you look at the 4-bit numbers, your range of numbers that you can represent in sign magnitude form is going to be as low as -7 and as high as +7. That's it. With 4-bit numbers, you can represent +7, -7, and between that range. In general, if you had n bits, then your range will go plus and minus 2 raised to n minus 1 minus 1. So there is n minus 1 in the power of 2, and then minus 1 is separate. I want to point out that we are losing. So if you have 4 bits, we will only have 15 unique numbers. We will not have 16 unique ones because of the sign magnitude representation having a problem of 0 with two same representations. Now, the one thing that I want you to take away from this slide is what is crucial to signed representations. What is critical? Critical to signed representations. The answer to that is the number of bits. Because think about this. If I told you that the number of bits are limited to 4, then you would read this as plus 4. If I told you that the same thing is limited to 3 bits, you would read this as -0, right? Because the first bit is sign and the next two are magnitude. So what is crucial in all signed magnitude representations is the number of bits. That needs to be made very clear, and that needs to be explicitly mentioned, because only then you can look at the most significant bit position and look at its sign, and then the remaining will be related to the magnitude of the number. All right, let's move on here. We already talked about this. We talked about how to represent 0 in sign magnitude. That's a problem, right? 0. So before this, whenever you see a question like this in sign magnitude, the first thing that should come to mind is how many bits, irrespective of the next step. You have to ask that, how many bits do I have? So let's say the answer to that is 3 bits, right? Then you can start answering the question itself. Represent 0 using 3 bits in sign magnitude. So plus 0 and minus 0. This, by the way, is in decimal. This, by the way, is in binary. So both plus 0 and minus 0 have two different representations in signed magnitude form, which is not that good, right? We are losing one possibility here, one combination here. How do I represent negative 56 in decimal in signed magnitude form? Well, again, how many bits? So let's assume 7 bits. What is the sign going to be? I have negative, so the first sign bit becomes a 1. Fix that. Then separately try to convert 56 base 10 to binary. We have to use 6 bits to do this because the 7th bit is for sign. If you do that exercise, I think you will get 1 1 1 0 0 0. 6 bits representing 56. So you just pad that up from here. 1 1 1 0 0 0. And that would be in binary sign magnitude form. 7 bits? Yes. Sign is there? Yes. Number is there? Yes. Sign is there, magnitude is there, and we have a 7-bit representation. There's a question over here. Let's see this. Yes, absolutely. We can keep changing the number of bits. So there's a question that if we wanted to use 1 byte or 8 bits to represent this number, 1 byte equals 8 bits. If you wanted to use something that is very commonly used, powers of 2, right? 16 bits, 32 bits, 64-bit computer, 8 bits, then we would so I assumed it was 7, so this is a correct answer. If I assumed 8 bits that I'm using to represent this number, then I would do exactly what you said. 1 for sign, followed by 0 1 1 1 0 0 0. Yes. So it depends on how many bits do you have allocated to that form. Let's now see whether sign magnitude addition works. Over here, I have 4 possibilities. I am separating them out as, so in all of them, I'm trying to add 4 and 3, but I'm playing with their signs. Both of them are positive here. Both of them are negative here. So operands have the same sign. And in the bottom two, the operands have a different sign. So for example, over here, 3 is negative, over there, 4 is negative. But I'm in all of these, I'm doing a addition while representing these numbers in signed magnitude form. So when you do this, let's see over here. 4 plus 3, expected answer 7. Now when you actually do this using the binary, what do you have? Plus 4 plus 3. You add the numbers. So when you are adding the actual magnitudes, you go ahead and add the magnitudes. But for the sign, you have to do a slightly different thing. We don't add the signs. For the sign, we are just going to use the same sign as the operands. The operands right now are positive here and negative here. So in the case where they are positive, we are going to use a positive for the result. In the case where they are negative, we are going to use negative for the result. Then you can read out the answer. 0, 1, 1, 1 plus 7. 1, 1, 1, 1, negative 7. It works out. Let's talk about operands when they have a different sign. What happens then? Well, over here, we need to do something special for the sign of the result as well as to compute the magnitude of the result. For the sign of the result, we need to compare the two numbers, and then the sign of the operand with the larger magnitude will be the sign of the result. So essentially what this means is we need a comparator to be able to compare the two numbers, and whichever one is the highest, that will dictate the sign of the result. We need a comparator. So for example, over here, 4 is positive, so the answer should be positive. Over here, 4 is negative, so the answer should be negative. That's as far as the sign is concerned. However, for the magnitude, we do a subtraction operation. So essentially, as we did the binary subtraction using the full subtractor table before, we would exactly do the same way with differences and borrows over here, but only for the 3 positions. We would not subtract or add the sign bits. That is very critical to note here. So all of this is done to be able to add things correctly using sign magnitude. Well, that's a pain, don't you think? I need something to, compare the numbers. I need to know which one is higher, which one is lower. I need to be able to add the numbers here. I need the ability to subtract the numbers here. So essentially, if we need to do this addition right with sign magnitude, we need a comparator, we need an adder, we need a subtractor. So lots of circuitry is needed to be able to do this right. So that's a disadvantage of this particular representation form, the sign magnitude. Yes, you would ignore the last borrow in the subtraction. How about when we do subtraction in sign magnitude? Again, we are dividing things up in the same way. Over here, we have operands of the same sign and then operands of the different sign. So 4, 3, subtraction, negative 4, negative 3, subtraction, different sign, 4, 3, so 4 minus 3, subtraction, negative 4, 3, subtraction, right? So we are all doing subtraction, but the sign of the operands is same over here in the top and different at the bottom. So different set of rules here. How do we do the sign of the result? Again, we don't subtract the signs. Sign of the result is computed the same way as we did for addition with different signs, which means go back one and take a look at what we did here. The sign of the operand is the larger magnitude. Whichever is larger, that will dictate the sign of the result. That's what we are going to do over here. 4 is larger, positive. 4 is larger, negative. Next, how about the magnitude? We just do the subtraction. So for the subtraction of the numbers, the magnitude, we subtract. The sign, we adjust the same way as we did for addition with different signs when operands had different signs, meaning we need to use a comparator. Now when operands have different signs, the two cases at the bottom here, the sign of the result is the sign of the first operand. So the first operand over here is positive, so positive. The first operand over here is negative, so negative. The one thing that I would say is if you end up with a case like this, where you are doing -4, -3, if the problem is posed as -3, -4, just put the bigger negative number at the top. Magnitude of the result, we just do the addition. So for the magnitude, we are doing the addition. For the subtraction, we are using the sign of the first operand. Again, to be able to do the subtraction, we need to do we need an adder, we need a subtractor, we also need a comparator. So lots of circuitry required to do addition and another set of circuitry required for subtraction. Now, all of this, we have not even talked about whether our addition and subtraction results will be correct or not. Because if you can see 5 and 3, I can represent 5 using 4 bits as 0, 1, 0, 1, that's sign magnitude. 3 is 0, 0, 1, 1, so that's my sign magnitude, sign magnitude. I've represented those bits, those numbers 5 and 3. But when I add them, my expected result was 8. However, what did I get? I got plus 0. That indicates an overflow condition, which means my answer is incorrect, invalid. I cannot do this addition correctly. However, if it was 5 plus 2, it would have been okay. No overflow there. Why is that? The reason is, we said with 4 bits, I can represent, with 4 bits in sign magnitude, I can represent numbers that are between +7 to -7. So if you have the numbers that are being added that belong to that range, for example, 5 and 3 belong to that range, but the answer is outside of this range, then you cannot represent it using 4 bits, which is the indicator of an overflow condition. Also happening over here. When you have -5, -3, you would expect an answer of -8. But what you are actually getting after you do the sign magnitude operation is -0 instead of -8. And a quick check for sign magnitude specifically about when this overflow condition happens is by looking at the carry into the sign position that is highlighted in red. So if the carry into the sign position is a 1, it indicates an overflow condition. If the if the carry into the sign position is 0, like the bottom two examples, that indicates no overflow. And you can validate that by looking at the result. The result 7 and -7 falls into this range of +7 to -7. Again, that range is directly related to the number of bits. 4 bits has the range +7 to -7. 5 bits would have +15 to -15 and so on.
So if the result falls outside of the range of numbers that you can represent using those n bits, that indicates overflow condition, and it can be monitored for sign magnitude form specifically by observing the carry into the sign position that is summarized at the bottom of this slide. So that's an overflow condition. We don't want to incorporate, we don't want this condition to happen. One way to prevent this condition from happening is to do a sign extension, which means that you can do a addition of one more bit possible for the answer. So for example, 4 bit plus 4 bit, if you allow 5 bits for the answer, then you will be able to get the correct answer. But we are not going there, but I just want you to know that there is a way to overcome this problem in certain situations. But right now, we are looking at cases where we are fixing the number of bits for the actual numbers being added or subtracted, and also for the answer. So let's take a look at some summary of the sign magnitude representation. The addition required many things. What was that? We needed a comparator to compare magnitudes. We needed a subtractor. We also needed an adder. The subtraction arithmetic for sign magnitude representation. We needed a subtractor, we needed an adder, we also needed a comparator. So essentially, we are complicating this, but the implementation is complicated because we need all of these: an adder unit, a subtractor unit, and a comparator unit. It is actually, when we look at the next form of representation, which is 2's complement, it turns out that you don't need so many units. Actually, you can just do an adder unit, and that's it. It will take care of subtractor and comparator and all of that. And we are about to end in just a couple of minutes. So what I'll do is I will set up the motivation for our Monday's class. If I'm doing a plus b, then I just do a plus b. Represent a in a 2's complement form, represent b in 2's complement form, add them up, and done. But if I wanted to do a minus b, then what I would do is I would still do the addition. However, I would represent b in its negative 2's complement form. And we'll talk more about this on in the next class. So essentially, that's how we avoid the use of a subtractor unit and a comparator unit when we go from sign magnitude representation to 2's complement representation. All we need is an adder. So this is called, uh, we are not actually doing the subtraction. Subtraction is being represented as pseudo addition. So all we need is the ability to do 2's complement and an adder unit. So that's where we will pick things up on Monday, June 1st. I hope to see all of you over there. And that's it from me for today. Questions, comments?